telling us about.
When am I supposed to be finished, like at the...
5:05 originally, but it'll be 5:10 since we started on the day.
So maybe, yeah, so let's just do like one of the exercises, and if there is time, we can just get back to the exercises at the end. So how about we do exercise number 3? Has everybody had a chance to look at the exercises, I guess?
Can we go non-sequentially?
Sorry?
Can we assume one?
Sure, yeah. So let's even forget about the first part of exercise 3. Let's just see what we get for bivariate multi-affine polynomials, right? So the question is, you have a polynomial of this form, and you can also assume exercise 1, I guess. So when is such a thing log-concave?
I mean, if you actually write down the Hessian, you get this following matrix, minus b squared.
So do you want to?
No, maybe.
So you're writing the Hessian of the log?
Log.
Yes, okay. So the Hessian of log of g is, okay,
After a constant, minus b squared.
minus, so d squared here.
C squared at the bottom right.
Okay.
And BC minus AD.
I think that's right. Okay. So first of all, when we are dealing with a degree 2 polynomial, complete log-concavity is the same as just log-concavity. Because if you take one more derivative, you get like linear polynomials. For those, log-concavity is just trivial, right? So you just have to check that this is, the constant of proportionality here also depends on the value of your polynomial and stuff like that. So it's not a constant matrix. Okay, but it's always a positive scalar of this, right? And you can again observe that this is a matrix with a positive trace, right? So you only have to check the determinant again to make sure that both of the eigenvalues in this case are positive, because you're taking the negative of this thing. So you want both of the eigenvalues to be negative, right? So you want exactly d squared times c squared to be bigger than bc minus ad squared, right? So I can just take a square root of this, and I get dc bigger than bc minus ad, which is basically the same as
Don't you want negative like other side?
Sorry, did I?
That's B on the top left.
Yeah, this should be b, yeah. Sorry, go ahead.
The inequality of the other one? Determinant.
So you want the Hessian of the log to be negative semi-definite, right? So I'm not working with the Hessian of my polynomial this time.
Yes.
I'm looking at the Hessian of the log of my polynomial, which is this thing times, I think, or divided by g or something like that.
So trace is negative.
So trace here, yeah, if you're talking about the negative of this matrix, the trace is negative, yes. If you're talking about this matrix without the negative sign, trace is positive, and you want both eigenvalues to be also positive, so that when you negate it, the whole thing becomes negative semi-definite. So again, you can just check the determinant, and you get BC bigger than BC minus AD. And you can also check that AD has to be the absolute value of BC minus AD. And this is equivalent to basically AD being less than twice BC. Okay. So if you remember, you had an exercise. I don't know if you went over it or not, but during Cheyenne's talk, you had an exercise to check when this thing becomes real stable, right? So does anybody remember what the condition for real stability was?
It is less than BC.
Yeah. So this is the condition you need for being completely log-concave. For real stability, you need AD is less than BC. So this already tells you that there are things which are completely log-concave but are not real stable. Right? So the last part of the exercise, it's an inequality that was first, I think, observed by Juniha and Botang Wang for Metroids. So now we want to use that inequality to basically prove that some approximate version of negative correlation is satisfied, right? So you want the probability of I and j being in a set S when S is selected according to a completely log-concave polynomial to be less than twice the probability that I is in S times the probability that j is in S. So any ideas on how we can prove this?
Plug in one all other coordinates.
Yeah. So if you look at the generating polynomial of mu, you can plug in a value of 1 for every coordinate except for zi and zj. Okay. And then the result that you're going to get is going to be a bivariate polynomial, which is going to be of this form. So the result that you're going to get is going to be of this form. Probability that I and j are not in S plus probability that I is in S, j is not in S times zi plus probability that I is not in S and j is in S times zj plus probability that both of them are in S times zi times zj. Now you just apply that thing over there, and you get actually something stronger than what I've written over there. You get something slightly stronger than the negative correlation up to a factor of 2, but it implies negative correlation up to a factor of 2. So I should maybe mention that so relaxed versions of negative correlation are something that Peter and Juni have studied. I think that you call it C. Riley or something like that. Yeah. So I don't know. So it's an interesting basically object to study what you can get just from approximate negative correlation, not complete log-concavity. All right. So let's skip the exercises for now and let's get back to the talk, I guess. So now we've completed this picture. We now have a candidate for this, completely log-concave distributions. So what I want to show next is that their supports are exactly Metroid-like objects. Okay? So what we have shown so far is that if you have a Metroid, the uniform distribution over the basis of a Metroid give you a completely log-concave distribution, but I haven't shown you the reverse, right? Okay. So let me let's quickly do this. So the support of a distribution is always going to be. So for now, we are only looking at homogeneous polynomial. So let's say that G mu is dehomogeneous and it's also multi-affine. Okay. And we want to show that basically support of mu is a collection of bases of Metroid. Okay. So to prove this, we're going to use basically this geometric characterization of bases of Metroids. So what is the support going to look like here? The support is going to be on a slice of the hypercube, right? So you look at basically all this set, which is basically all 0, 1 vectors, where exactly you have d1s, right? The support of mu is going to be a subset of this. Now there is a geometric characterization for when subsets of these things become bases of a Metroid. And that geometric characterization is this, that if you look at, so the indicators of bases, for all of the, so look at the indicators of bases when B is in S, and look at the convex hull of this indicator bases. So convex hull of these things when B is an element of S, or sorry, right? It's going to be some polytope supported on the affine slice of the hypercube, right? So every So in this polytope, you're going to have a bunch of edges or one-dimensional faces. You get a Metroid exactly when these edges are the difference of two standard bases. Okay. So whenever basically B is connected to, so Metroid, if and only if, when B1 is connected to B2 in polytope, then the indicator of B1 minus the indicator of B2 is some EI minus some EJ, where EI and EJ are elements of the standard basis. Okay. All right. So now one thing that you can show using, this is basically very similar to the proof that the supports of real stable polynomials are Metroids, almost the same. So it's not a very innovative proof, but let's just go over it. So the point is that if you look at this polytope, it's the Newton polytope of your polynomial, right? If you restrict your polynomial and drop the terms that don't belong to a face, so let's say that f is a face of this polytope, and you look at basically the polynomial g mu restricted to the face, which is just the sum over basically the mu of b, z to the b, where b is inside this face. Okay? So we're going to show that this polynomial also is completely log-concave, okay, for any face, no matter what. And when you prove this, you can restrict to a face which is an edge. Right? So when you restrict to an edge, it's going to be of this form, z to the b plus, or z to the b1 plus z to the b2. Right? And when is this going to be log-concave? You again need the connected supportness for this to be log-concave, right? So let's say that B1 and B2 are two elements such that their symmetric intersection is bigger than 2. If the symmetric intersection of B1 and B2 is exactly 2, the difference of their indicator vectors is exactly the difference of two standard basis elements, and we're done. So let's say that these are, this symmetric difference is bigger than 2. Now you can look at basically so define basically C to be the intersection. Or if you want the indicator of C to be the element-wise minimum of B1 and B2. Right? Now, if you differentiate with respect to elements in C, right? What you're going to get at the end is going to be, so start from this polynomial. This is G of mu restricted to the face F. So when you differentiate basically with respect to elements inside C, this polynomial G mu sub F, what you're going to get is Z to the B1 minus C times Z to the B2 minus C. Added with Z to the B2 minus C, right? But unless both of these are of size 1, this is a sum of two polynomials, and the whole degree is bigger than 2. So this was not allowed, right? The connected supportness was not allowed. So you're going to get something which doesn't have connected support, and it's not going to be completely log-concave. So all I have to show you now is that when you have a face of this polytope, if you restrict your polynomial to the face, then complete log-concavity is preserved, right? And this is also easy to show because, okay. So let me just erase this. Okay. So first of all, you can basically show that if you have a transformation going from Rn to Rn, and your transformation basically takes the positive orthant to the positive orthant. So this is basically a slight strengthening of the fact that when you do affine transformations on the input, log-concavity is preserved, right? I'm just saying that complete log-concavity is also preserved. You can just verify that because when you have an affine transform, when you're taking derivatives of this, you can just apply chain rule, right? And just take the derivatives through. So what I'm saying is that when you're taking dv1 up to dvk of, so your affine transform is always of this form. T of x is equal to ax plus b. And A has positive entries. B also has positive entries. So that's what I mean by the positive orthant being preserved. You can just check that this is equivalent. So when you apply a bunch of directional derivatives to basically GOT, using chain rule, you can write this as basically partial derivatives along AV1 up to AVK applied to G composed with T. Okay. Now, if V1 through VK were elements in the positive orthant, AV1 up to AVK would also be elements in the positive orthant. So this thing is completely log-concave. And then when you of course apply a affine transform on the input, log-concavity is preserved. Right? So okay, so you can do affine transforms on the input, and complete log-concavity would be preserved. Now, how do I use that to prove this? I'm going to apply basically a simple transformation. I'm going to apply, so T of Z is going to be, so let's call it this one. So I'm going to just multiply each variable by some number. Okay. So these numbers, I've represented them in a funny way as e to the tw1 up to e to the twn. What's the point of this? The point of this is so the point of this is that GOT would become the sum over all mu of s, z to the s, times e to the t times the product of w and the indicator of s. Okay, so that's how those scalars come out, right? And now if you look at a face of your polytope, there is some vector w. So for a face f, there exists a vector w such that the face is basically the argmax of inner product with w. The convex hull of the support. Right? So the scalars are really maximized at the points on the face, right? So now if I divide the whole thing by this maximum value and let t go to infinity, every term goes to 0 except for the ones on the face, right? So because complete log-concavity is a property that's closed under limits, you get the polynomial restricted to the face. So this is a proof that that basically the supports of these things are also Metroid-like objects. Okay. Any questions here? Yeah.
So it sounds like you could do this argument and show that if you're not multi-affine, then this is the support of the poly matroid. Is that right?
So when you're not multi-affine, the support is not a Metroid, but it's basically a generalized permutahedra.
Polymatroid, right?
Yeah. Exactly. I was going to show that towards the end of the talk. Okay. So let me switch gears up a little bit. I briefly glanced over this conjecture of Mason on the independent sets of Metroids. Let me just mention that again. So in the beginning of the talk, I talked about log-concave sequences and how they are prevalent all over combinatorics. One of the sequences that used to be conjectured to be log-concave, but now is proven to be log-concave, is when you take a Metroid M and you look at the sequence of basically I0, I1 up to I to the rank, where Ik is basically independent sets of size k. Okay. So it was conjectured to be it was conjectured that this sequence is log-concave. A proof of this was first given by the reference here, Schroeter and Wank. But there is also a stronger version of this conjecture, which is also due to Mason, which was not resolved by this conjecture. So this stronger version says that when you divide these by binomial coefficients, you still get a log-concave sequence. So now that we have developed all of this theory, I think a cool application to see is that you can easily get this, okay, the strongest form of the Mason's conjecture. And this is exactly what we did, and also Peter and June did in an independent work. So I showed you that the generating polynomial of basis of a Metroid is completely log-concave, but what you can show is that there is a different polynomial associated to a Metroid, which is also completely log-concave. Okay. So the polynomial is of this form. You sum over independent sets this time, instead of bases. You take the product of zi's where I is in the independent set, but you homogenize this to degree n with an extra variable y. Okay. So if you want to prove the complete log concavity of this thing, you can exactly use the previous machinery. Okay. Turns out that, again, you have to only prove this for matroids of rank 2. And for matroids of rank 2, you can just write down the Hessian and observe that this is the Hessian is a rank 1 matrix minus a PST matrix, and everything works out. Okay? So once you have the complete log concavity of such a thing, how do you get the ultra log concavity of this sequence? So it's an easy exercise. You just plug in the same variable z for all of the zi's. Okay. So the bivariate polynomial you're going to get by doing that is exactly I0 times Z0 y to the n plus I1 Z1 y to the n minus 1 up to basically I rank Z to the rank y to the n minus rank. Okay. And for homogeneous bivariate polynomials, we already observed that complete log concavity is equivalent to the sequence of coefficients being ultra log concave. When you divide by the corresponding binomial coefficients, you get an a log concave sequence, right? So that's basically, once you have all of this machinery, that's a one-line proof of the strongest form of this. And this is also basically the equivalent of what Peter and June also did. So why am I showing you this example? This is an illustrative point where you basically see that this is to illustrate that complete log concavity is not about the roots. Okay. So if you're familiar with real stable polynomials, when you have a real stable polynomial like this, which has a factor of y, right? So you can just basically factor out y to the n minus rank, which is the minimum degree with which y appears in this polynomial here, times some other polynomial in y and z, right? So let's call this other polynomial h of y and z, right? When you have a real stable polynomial and you factorize it in this way, each of the two sides has to be also real stable, right? Because when you don't have roots in a certain region, none of the factors can have a root in a certain region, right? So complete log concavity cannot be about the roots because the polynomial here would not be completely log concave. If it was, you would get something stronger than the log concavity of this sequence. You would get basically the binomial coefficients with n minus rank replaced for n. And you can just observe that even for like the uniform matroid, that's false. The uniform matroid on n elements with rank. Okay. So completely log concave polynomials don't have this property that when you factor them out, each of the factors is completely log concave, and that's why this is really just going beyond the roots. Okay. All right. So that was, I showed you two polynomials for matroids which you can prove are completely log concave, but of course the machinery is there to prove other things. So here are some of the other things that you can prove are completely log concave. So something that also Peter and June showed is that the random cluster model. So this is in the graphical matroid case, this is this distribution. You start with a graph, you select a subset of it, and then the probability of selecting that subset is going to be proportional to basically some parameter q to the number of connected components imposed by that subset times the independent distribution. So you can think of this. So sample edges independently of each other, each with probability p, And at the end, multiply the probability by q to the number of connected components. Okay? So there is an analogous thing for general matroids. I'm not going to mention it. But you can actually show that this thing for q between 0 and 1 also satisfies complete log-concavity.
It's a top polynomial, right?
It is a, so that if you're familiar with the Toth polynomial of the graphs or matroids, this is basically a transformation of the Toth polynomial, exactly. So again, the machinery just boils down to checking this for matroids of rank 2 and everything works out. So the significance of all of these is for sampling algorithms, which I won't mention at all today. We're going to see them later on in the semester. So if you care about determinantal point processes, so here is something that is also completely log-concave, but not real stable. Okay? So in a determinantal point process, remember that you had like these PST matrices. An alternative description is you have a bunch of vectors. You select a subset of them with cardinality equal to the dimension of the space. And each subset you select with probability proportional to the determinant spanned by those vectors. Okay? Squared. So that distribution is real stable. And it was important in machine learning because it has this repulsive property that you tend to select vectors which are far apart from each other. Okay? So now if you want a knob on the diversity, you can raise this determinant to some power between 0 and 2. And turns out that for any power less than 2, this is going to be completely log-concave. This is actually true for any other distribution that's completely log-concave. If you start from, if basically mu is CLC, then mu raised to the power beta for beta between 0 and 1 is also CLC. So again, this gives you a knob on the diversity. And this is so this goes back to the point that Federico was making. So I told you about the multi-affine homogeneous case. So the support of CLC distributions in those cases are always bases of a matroid. You can ask what is the general case. So it turns out that you can reduce everything to multi-affine homogeneous polynomials. I think exercise 1 tells you how to homogenize, and there are other things that you can do to make things multi-affine. So if you do all of that, what you get is that the support is always going to be of this form. Take basically a polytope whose vertices are integer points and whose edges are either parallel to the standard basis or parallel to the difference of two elements in the standard basis. Okay? So these are a slightly larger class than generalized permutahedra, and the support of any CLC distribution is going to be of this form. And moreover, for any polytope of this form, there is going to be a CLC distribution supported on it. Okay? So the CLC distribution supported on this polytope is basically a truncation of the Taylor expansion of e to the x. Okay, so that's the way I like to think about it. So if you look at basically e to the x1 up to xn, this has some Taylor expansion, right? By the way, this is not a polynomial, but you can see that it's CLC. If you take any number of derivatives of it, it's going to be a multiple of itself, and then when you take the log, it's going to be a multiple of basically a linear function, which is concave, right? So that statement is saying that when you restrict the Taylor series to points inside such a polytope, okay? So sum over, yeah, I've written it down here. So sum over only integer points inside the polytope of whatever you get in the Taylor series of e to the x. This thing is completely log-concave. Okay? So when you're talking about 0, 1 polytopes, this is the generating polynomial of the uniform distribution. When you're talking about higher powers, you have to include the factorials. Okay, so all right, so let's. So that was basically the last slide that I had. I have So I have 20 minutes for the open problems, or should we give a break, or?
Maybe like a 5-minute break, and then you actually have like half an hour.
Okay, yeah, that's good. So so in the open problems, I might still continue a little bit of a lecture, but yeah. So there is one open problem for which I have to explain some things, but yeah. So should we just take a 5-minute break, or yeah?